Hello pre-calculus students, this is Miss Robinson, and today we are going to be beginning our section 5.2 notes. So go ahead and flip open to your section 5.2 notes. This is one-to-one function and inverse functions. So we're going to begin with some vocabulary and definitions. So first of all, a one-to-one function, as we read here, is a special type of function. So we would say a function is a one-to-one function if any two different inputs in the domain correspond to two different, keyword is different, outputs in the range. That is, if x1 and x2 are two different inputs of a function f, then f is a one-to-one function if f of x1 is not equal to f of x2. This essentially means that no input, no x, no value in the domain can share an output or a value in the range with another x. So you can't have two x's with the same output or two inputs with the same output and have it be a one-to-one function. Okay? The best way to do this is to look at these examples. So if you look at these examples, we see that in these mapping situations, that's what we call this, every single item that I have in my input here maps to exactly one output. So Indiana has its own, Washington has its own, South Dakota has its own, North Carolina has its own, and Tennessee has its own. None of them share the same output value. Therefore, I would say that this relationship is one-to-one. And if I were to create a function out of this, this would be a one-to-one function. But let's look at this other example over here. Over here, I see that dog and cat both share an output of 11. Duck, lion, and pig all share an output of 10. And then rabbit has an output of 7. Now, this is not a one-to-one function because I have two in my domain that share the same range value, the same output, or same here, I have 3 in my domain, or 3 x's, that share the same output value. So we're repeating. We have more than one input that have this same output. That's a problem, so this is not a one-to-one relationship or function. Okay, so one-to-one just means that for every one input value, you have to have one unique output value. And when I say unique, I mean that it's the only output value, or its output value is different from all other output values. Okay. Unique to that input. Alright, so that's just a definition of one-to-one. We'll see how we need to use that in a little bit. Okay. Now another way, if we don't have these mapped out for ourselves, like in these diagrams up here, to see if we have a one-to-one function is to use what we call a horizontal line test theorem. So if you remember in Algebra 1, we had the vertical line test, right? And we carry that through quite often to see if something is just a regular function. This idea works the same. So in a vertical line test, I take a vertical line and I drag it across my function and see if my line intersects more than once. If it intersects more than once, then it's not a function. This is the same idea here. So if every horizontal line intersects the graph of a function in at most one point, then f is one-to-one. So I take my pencil or some horizontal line and I move it across my graph. This time I'd be moving it up and down since it's a horizontal line. If I intersect in more than one spot, then I do not have a function, or I do not have a one-to-one function. So if I look here, I take horizontal lines here across, and for all of these I am intersecting twice. That means that two of my x values share the same y value and therefore this is not a one-to-one function. So if you think about it, with a horizontal line, my y is the same, right? I would have the same y value for any point on a horizontal line. So that tells me if it intersects a horizontal line, then those spots where it intersects have to have the same y value. And we said earlier that if an x shares a y value with another x value, then we do not have a one-to-one function. Okay, so this is an easy way to test if you have a one-to-one function by graphing. So we could graph it, use a horizontal line, tell if we have a one-to-one function or not. Okay. Alright, so that's the horizontal line test theorem. Now let's go on to define an inverse function. Okay. So suppose f is a one-to-one function. So we know that what that means earlier. That means that every x has only one unique y. Then, to each x in the domain of f, there's exactly one y in the range. Okay, that's what we just said. And to each y in the range of f, there is exactly one x in the domain. Okay. The correspondence from the range of f back to the domain of f is called the inverse function of f. Okay. So what this is telling me is that if I have a one-to-one function, meaning that for every x there's only one y, and for every y there's only one x, one for each, then I can have this idea called an inverse function. And this inverse function just means that I swap my domain and my range. So this time, instead of going from the domain, so inputting the domain and getting out the range, we are going to go from the range to the domain. So we're going to input the range and get out the domain. Okay? So we're switching our x and y's, or our inputs and outputs, and we call this the inverse. Okay? So if we think about this, we're just taking all of our points. So this is a little tough to see, but this is the point B, A. And we're flipping the inputs and the outputs, or the x's and the y's. So if I had B, A before, that B would become my new y value, and that A would become my new x value. So I would have AB. Same would be if I started with AB. If I wanted to find the inverse, I would flip my x and my y, switch those two values with each other, and I would get B, comma A instead. Okay. So this inverse function really just means we're replacing the domain with the range and the range with the domain, flipping the input and the output. Okay. Now, graphically, we can actually see this occurring. When we graph, we can see the relationship between inverses. So the graphing inverse functions theorem tells us that the graph of a function f and the graph of its inverse, f inverse, that's what that f to the negative 1 power means, f inverse, are symmetric with respect to the line y equals x. So a graph and the graph of its inverse should be symmetric across the line y equals x. And if we see up here in this example, right here, I can see that if I were to reflect this point, AB and BA, across this line y equals x, they would be the same distance away. Well, we said that an inverse function is switching the y and the x, right? So it would make sense if we have y become x and x becomes y, that we're just flipping across y equals x. Okay. So that means that, again, anything that was an x becomes a y, anything that was a y becomes an x. So we're just switching the two, y and x. The same should be here. So both of these should be the same distance away from this y equals x line when we graph a line and its inverse. Okay. So for this point, when I want to find the inverse, I have my x value. I believe this says A3 and B3. So my x value would be B3, and my x value would be A3, and my y value would be B3 here. So if I want to find the inverse, I'm swapping the x and the y. So my y value should now be A3, and my x value B3. And you can see here that this is the same length as this one, and this here is the same distance as this one here. Okay, so if we flip across these, you can see that their distances from this line should be the same, and we're just flipping the rectangle that makes this point. Okay, so we're taking this and we're moving it in this direction so that the x becomes the y and the y becomes the x. And we do this with all of these points. So you can also see that here, originally this would be A2 for x, B2 for y. So when I flip that across y equals x, or I flip my x and y values, I'm going to have B2 as my x and A2 as my y. And for my last point, if I start out with A1 and B1, then my x becomes my y, so my y would be A1, and my y becomes my x, so that would be B1. Okay. So, flipping our x's and y's, the important thing to know about this is that, judging by this diagram here, if I just learn how to graph my function, and then graph the line y equals x, I can reflect all of my points and my motions across y equals x and have a graph of my inverse without graphing my inverse. So though we can switch the y and the x like we talked about before for the inverse function, we can also sketch the graph by reflecting across the line y equals x. And we'll see that in some examples in a bit. Okay. Next will be example 1, so make sure you go to that video next. Thank you. We are going to move on to section 5.1, example 1 now. Okay, so example 1 has 2 parts. For both of these, we want to determine whether the function is 1-to-1. So remember we said that a function is 1-to-1 if there's only one x for every y and one y for every x. So the relationship between these should be unique. There is a unique y for every x and a unique x to every y. Okay. So if we look at this first function, we have this mapping diagram, and we see that 38 maps to 57. The age 38 maps to the cholesterol level 57. The age 42 maps to the cholesterol level 54. The age 46 maps to the cholesterol level 34. The age 55 maps to the cholesterol level 38. And the age 61 also maps to the cholesterol level 38. So I could see very easily here that these two inputs, or these two parts of my domain, share the same output, the same value in my range, meaning that this relationship is not unique. These share a range value, so it is not 1-to-1 value. Here we have 2 inputs to 1 output value. So we would say that this is not a 1-to-1 function, because we're not mapping 1 input to 1 output in this instance here. Okay? So that's A. B, this time I have some points. Let's zoom in a little bit on this one right here. Okay, so I have the point -2, 6, -1, 3, 0, 2, 1, 5, and 2, 8. So I need to look and see, does every input have only one output? So do any of my values for my inputs share this same output? And I see here 6, 3, 2, 5, 8. None of those have the same output value. So that's telling me that every input that I have here, -2, -1, 0, 1, and 2, has its own unique output, does not share with any other input. So that means that for every one x value I have here, or every one input, I have one y value, or one output. So then I can say that this is a one-to-one function or relationship here. Okay, so because every one input has only one output, none of them share the same output, I can say that this is one-to-one. Okay, that's example 1. Let's continue on to example 2. Let me zoom out a bit for this one. Okay, so example 2 gives us a graph of a function and then asks us to use the horizontal line test to determine whether the function is one-to-one. Okay, so remember, horizontal line test, just like the vertical line test, except this time we're taking a horizontal line. So we're going to take a horizontal line, for instance our pencil, horizontally, and we're going to drag it across our graph, the graph of our function. So for A, I'm going to take my pencil and I'm going to go up and down along the graph of my function. Now, if this vertical line, this horizontal line crosses my graph in more than one point, then I do not have a one-to-one function, because that means that I'm sharing y values. So here I can see at all of these values, anywhere here, every x value here and here, here and here, here and here, shares a y value, right? Those have the same output value. So I'm not passing the horizontal line test, so this is not a one-to-one function. When I take my horizontal line, it crosses twice in many different places. So if my horizontal line crosses more than once, it is not a one-to-one function. Okay. For B, so I'm going to do the same process. I'm going to take my pencil and I'm going to move it down across my graph and up, and I'm going to ask myself if I cross in more than one spot. So if I draw this, I can see that here, 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 here. Very obvious that I'm not crossing my function more than once. I could get a little confused at this point. However, if I look very closely, I can see that this is really only dipping to that straight area for an instant. There's not more than one point where it is straight here. There's just that one point, and then it moves back to being curved up again. So even here, I'm only going to hit that 0 one time and then move across. And as we know, for an x cubed function, there is only one moment when we have y equals 0, when we have x equals 0. And this is very similar to a cubed graph, so we might assume that it is. Either way, if I take my horizontal lines and I go across this function, I will not intersect it more than one time, meaning that I do not have x's that share y values with one another. So if it passes my horizontal line test, if I'm only intersecting once with all horizontal lines, then I can say that this is a one-to-one function. Okay? Alright, so that's it for example 2 on our 5.2 notes. Now, to finish up these 5.2 notes, I want you to, at home, finish this last little section right here. This seeing the concept on this page. Now, your graph should have nothing on them. I've completed the seeing the concept already, but you just need to follow the directions here and graph each line and think about the questions and then write down a little blurb about what you observe. Okay? So it shouldn't take you more than maybe 5 minutes or so. So it's not very much else extra that you have to do, but you should have the seeing the concept when you come to class on Monday. We will be checking for it, so you need to have it done. It's also very important when we continue our notes on Tuesday that you have this done. Okay, so before you finish your notes, I want you to finish this seeing the concept, and then you are done. I hope you have a great weekend, or if you're at the end of your weekend, I hope you have a good Sunday night and Monday. I will see you in class. Thank you.